It's our week 2 calculus review homework. This is your lecture notes. I will post a PDF of this after I post this movie. So let's say that I have a function. So this is calculus review. X squared plus 4y squared equals 4. And the instructions are find dy for dx. All right. Well, hopefully you remember the whole implicit differentiation game. So it's easy. The first part's a piece of cake because it's already an x. We'll take a derivative with respect to x because this whole thing is y. The whole function, we're assuming that it's y. So dy dx, so this part would become 2x. I would treat 4y squared like it's an x thingy, giving me an 8y, but then I have to throw in whatever dy dx is. And the derivative of a constant is always just going to be 0. So that means I can solve this for dy dx. So 8y dy dx would equal negative 2x, which means dy dx is going to be minus 2x per 8y, which is just going to be a minus x per 4y. And that would be the dy dx of that equation. All right. Then what if we had a function like the sine of y equals x, and we wanted dy dx of that? Well, the derivative of y with respect to x of sine y would just be cosine y, but I have to throw that dy dx in there because I am differentiating with respect to x, and it's a y doohickey. And this would be 1, correct? So now dy dx, this is super duper easy, 1 over cosine y. Yay. Done. Let's say that we want dy dx for the square root of xy equals x squared y plus 1. Like, okay, Van Gilda, that's just wrong. You're evil, man. You're evil. Well, is it okay for me to skip over writing that the square root of xy is just xy to the 1/2 power? Can I skip writing that? I trust that that's okay. All right. So I'm just going to write at the derivation of it. All right. So if I take the derivative of y with respect to x for this first part here, I'm going to have 1/2. That's going to come down from that exponent. All right. xy, then minus 1 on that half, and I get minus half. But what's going to be next here? So I'm going to have, whoops, got to get my writing straight here. Guess I can put this in breakfast. I have to do the inside of that function, don't I? So a little chain rule action, and so x dy dx plus y. I hope everybody's up to speed on that little apply the product rule of it, what you call it stuff from calculus. So now we can go over to the other side. The x squared thing will be a 2x, but then I just times the y because I'm leaving that function alone. But then I'll leave the x squared alone, and I get a dy dx. So now I have dy dx in 2 spots, which means I got to get that together, do a bunch of algebraic maneuvers, all right? And I'm not going to bother with all of that because it's algebra, okay? But In the end, this one, dy dx, is going to be 4xy times the square root of xy minus y all over x minus 2x squared square root of xy. I don't think the one that I gave you in the actual homework is any more difficult. The hard part will be the algebra. All right. If you do this first part right, then it's just an algebra maneuver. All right. So there are a few times in the course where you'll need to do some gnarly algebra, but most of the time you don't have to. Yeah. Uh-huh. So when you're dy dxing that, since it's a product, the way that rule works out is you take it's either derivative times the other thing, then plus you flip what you do the derivative of. So the derivative, the ddx of x squared is 2x, but because it's multiplied by y, what I would do is if I take that derivative first, then I leave y alone, leave it as the product, but then I have to add the derivative of the second thing times the first thing. So it was derivative of the first thing times the second plus the first thing times the derivative of the second. That, yes. All right. Let's say that we have this position function, s of t. Since I used r earlier, I'm going to use s this time. Okay? Just for equal opportunity punisher here. So here's this function, minus 16t squared plus v naught t plus s naught equals, oh, that's just what it is. All right. So here's our position function. Now I'm using the same symbols as before, t for time. Position, our v for velocity. I have a v sub 0 as initial. That should be something that you did in calculus. And then s sub 0 be the initial position. So s of t is the final position at some time t. S sub 0 is the initial position at time 0. So here's our position function. It defines what we do. What if I wanted to find the velocity function of a freely fallen object whose motion, whose position at any point in time is described by this function? What would I do? Take the derivative. So that derivative, we call it speed. First derivative of a position function is going to be speed. It's ds dt. So this is us getting all crackly. All right, this is a crackulous lecture. ds dt. So what would I do? Well, this is easy. The derivative of s with respect to t just means, bring that 2 down, minus 32t. And guess what we do with the remainder of the terms? Nothing, right? Because initial speed would be 0, wouldn't it? And initial position would be 0. And one thing about 0 is its rate of change is 0, all right? So we just have, this is it. The first derivative of this big long function just ends up being one term. This should be old news. You would have done this early in Calc 1, first month or so probably, if memory serves me well. So now I've done it. I have the velocity function, all right? And I think the way you asked the question, find the position and velocity functions after I gave you the position function. All right, so that's an easy giveaway there. Now determine the average velocity on some time interval. So if t is on some interval, some say 1 to 2, then you know, v of t, what does it equal? Well, that should be fairly simple. You're going to have your, I guess, your ds per dt, so to speak. So speed would be your s at 2 minus your position at 1 over 2 minus 1, because I actually know the time values in that case. Now, I'm just going to give away the numbers because you could easily compute what the values would be when you put 2 and 1 into the box. But this is for when I forgot to mention, I'm sorry to do this. This was initially 1,362 feet. It wasn't 0. 0 is at the ground level. I'm sorry. But it's still, that derivative still would have been 0, the first one. So I just realized that I left that out of the reading off my notes here. So that means, given how that function plays out, you would have had 1298 minus 1346 over 2 minus 1, and that would give you a negative 48 feet per second, since we're dealing with feet here. Okay. So we would get, over that time interval, by plugging in the position change over the time change, we get this function. All right. Now, what about time to reach the ground? So if our initial position is 1362, how long to hit the ground? Well, this means that the position at that time to hit the ground is going to be 0 because it hits the ground, and VT is going to be 0 when S naught is 1362. So that means I have 0 equals minus 16t squared plus 1362. And if you do that fairly simple algebraic maneuver, you get the square root of 1362 over 4, which is roughly 9.226 seconds. If I want to carry all 4 of those digits that are specified in the one measure, I get to assume that I can have any number of sig figs for the constants. Constants, we kind of ignore them in sig fig land. All right? It's the other stuff that matters. And so we can use this approach here to get some basic stuff. This was mostly algebra with the exception of that derivative. So now let's do an antiderivative. So let's say, so it's a new problem altogether. So we have a particle moves on x-axis, and the speed function of this particle is just the is t to the minus 1/2, or 1 over the square root of t. All right. At time 1, x equals 4. So 1 second, x, the position is 4 meters. All right. Find acceleration and position functions for the particle. All right. So I have Vt equals t to the minus 1/2, and this will be for t greater than 0 necessarily. All right. So what will x of t be? Well, the other time I did a derivative. If I want to go the other way, I do an integral. So the position is the sum of all of the velocity time chunks. Didn't we get that from our other thing where the final equals initial plus change? Final position will equal the, in this case, the sum of all of the speed time changes, which will include that initial speed. So that means I'm going to integrate t to the minus 1/2 dt, and I'm hoping that this is an unsurprising result for you. All right, the antiderivative of that thing, the integral, Calc 1 level stuff. So now I have this x of t is this 2 to the t 1/2, and then I have that constant that's in there. And so basically, 4, x is 4. Let me get the color switched back here to what I had for that data. So when x is 4, t is 1, trying to write that where it goes, plus some other piece of this puzzle, inevitably a starting point. So what does that mean? That means that my value of c is 2. And so this means that my s of t position, I guess I could have, instead of using x, I could have been consistent with what I was saying above. S of t is going to be what? 2t to the 1/2 plus 2. That's my actual function for this particle, obeying that speed law under these time and position conditions. You surely did a handful of these in Calc 1. All right. Now the acceleration would just be the derivative of the velocity function. So that's going to be the time derivative of our velocity function. So I'm running out of space on the bottom of my screen here. So that means looking up, where is it? I want to take the derivative of that. So I'm going to have minus 1/2 t to subtract another one from that. So it's minus 3/2. So if I wanted to get rid of all that mess, I could just write 1 over 2 times the square root of t cubed. So we've done our duty. Yay.